Okay, this is a little strange when we get to section 8.1. So that's another reason I wanted to run those off for you, because you really have to invest some thought in this. It's not something you really have thought of before, but it's really integral to statistics. So first thing is, what's a sampling distribution? Well, you can read the definition here. It's a probability distribution for all possible values of the statistic, that means an average or a proportion, computed from a sample of size n. Now think about that for a minute. All possible values of the statistic computed from a sample of size n. So then we have a distribution based on that. Now we're talking about averages in section 8.1. So it's the probability distribution of all the values of the random variable. Now look at it, x bar. What kind of thing is x bar? It's the mean of different samples. So now then, we're going to take sample. Let's say we took a sample of 50. Then we get the average of that sample. Then we take another sample of 50, and we get the average of that sample. This distribution are those averages. They're not the individual people or plants or animals or anything. They're the average of different groups of size 50. Whole different breed of cat. Okay, here's what we're going to be doing. We're going to take an SRS of size n, let's say 50. We're going to get the average of it, and we're going to keep doing that over and over and over again. And notice the note down there. Once you've got a sample, it can't be obtained a second time. So no repeats for the different samples. Now, how many samples could I get from, let's just say, a population of 10? How many samples could I get of 2? The order doesn't matter. What does that turn out to be? 10 combination 2. How many? 45. Okay, thank you. So I could get 45 different samples of size 2 from a population of 10. You go, well, that's not bad. But notice the definition here. The distribution of all possible values. So I would have 45 different averages that I would get. Does that make sense? How about if my population was 100? Let's just do that. And I'm going to get 2. Thank you. Still a pretty small population. But once that population starts getting up, then we might run into some problems. Let's pick a bigger population. Let's say we found an island and there's 10,000 people on there. And I want to get samples of 40. Overflow on that calculator means it's too large of a number for it to store. Now, how am I going to get all of those? Because we know that calculator can go into scientific notation and say 10 to different powers. Can I get all of those? No. So I want you to realize right up front that this idea of a sampling distribution, except for real small populations, is just a theoretical thing. There's no way I can get all those samples. Billions and billions and trillions and billions and trillions and lions and tigers and bears. I can't get all of them. So, but the concept is what I want you to get. So what are we doing? We're sampling from a population. no repeats, and then we're getting the averages of each sample. And our distribution now is the distribution of the averages. Okay, let's keep going. How do you get the mean and standard deviation? It says here the sampling distribution of X bar has the same average as the population. So if I could take all those samples, the average of the averages would be the same as the population. So if I wanted to find the average height of all 18-year-old guys in Texas, all I got to do is take all these almost infinite number of samples and get their averages, and well, that's impossible. And it says the sampling distribution of X bar has a mean that's equal to the population mean, but here's the kicker. The standard deviation of this new distribution, you take the population standard deviation and divide it by the square root of the sample size. Now that formula is in your formula pages. So let's just do an experiment. Somebody give me 3 numbers. 54, 14. How many? 75. Okay, how many samples of 2 could I get out of that? Well, I could have 54 and 14. I could have 54 and 75. I could have 1475. So I could get 3 different samples of 2 out of that. Now, that's a really small population. What's the average of 54 and 14? 34? Okay, thanks. What's the average of 54 and 75? 64.5? How about 14 and 75? Thank you. Okay, now then, there's our sampling distribution of X bar. In other words, those numbers at the bottom are X bar. Y'all with me? That's a really tiny population. We can actually do this one. There wouldn't be any need to, but I just want you to see how it works. Now, what's the average of 34 and 64.5 and 44.5? What's the average of these guys? Say it loud so I can hear it.
47.66.
47.66. So it just keeps repeating?
Yes.
Okay, thank you. Okay, now what did we do? We got different samples. Did I get all the different samples of size 2? Yeah. Then I get the average of each sample. And then if I could put all those together, that's what this thing is telling you. The average of all those averages is 47.6 repeating. What's the average of let's go back to the population. What's the average of 54 and 14 and 75? That's what that's saying. If we really wanted to get the average of the population, all we got to do is get a sampling distribution of those averages. Well, that's great if you've only got 3. Why would you be doing that if you only had 3 things to start with? You wouldn't. But I want you to realize that this thing down here that we obtained from the different samples is exactly the population average. And that's what this is telling you right here. That's all it's telling you. The standard deviation, though, is what changes. Notice it gets smaller because I'm dividing by the square root of n, which is my sample size. So in this case, I'd be dividing the original standard deviation by the square root of 2 because that was my sample size. All right, makes sense so far? Okay, get rid of that. caution. For all the stuff we're talking about this morning, two things have to be true. The sample has to be random. So think SRS. Put all the names in a hat and draw them out. And the values have to be independent. Well, how do we even know that? Well, it tells us down here. If the sample size is less than 5% of the population, then we're going to assume that they're independent. So if I've got a population of 10,000 like we had in the first example, what's the biggest sample I could get? What's 5% of 10,000? 500? What's this mean? What's 1% of 10,000? 100? So 5% would be 500? So if I have a population of 10,000, the biggest sample I could have and still assume independence is 500. So now then we've got some restrictions on us. I want my sample to be large enough to be representative of the population, but not too large to make sure that they're, or at least to assume independence. So we good? So we're going to be looking at those two things. Do these different samples match up to that? Are they random and are they independent? Let's keep going. Okay, IQ scores, we see the mean, we see the standard deviation. So here's what the population graph looks like. I just put the mean in the middle and then I came off each side with standard deviations. But if I start taking samples of 9 and getting their averages and then figuring out that distribution, look what happens to this. That original standard deviation, 15, is being divided by the square root of 9. Yeah. Well, that means that 15 becomes 15 divided by 3. So look at this new standard deviation. It's 5. What does that do? It squishes that distribution together. It still has an area of 100, and we can still do z-scores and all that good stuff, but the standard deviation went way down. Okay, that's based on sample sizes of 9. And I want you to realize I put those drawings on the same scale. All right. Stop me if I'm going too fast. So you should be getting in your head, all right, once we start taking samples bigger than 1, the standard deviation starts going down. Mm-hmm.
How did we go from the wide graph to
The standard deviation of the population was 15. Once I start pulling samples of 9, what do we know? We know that the standard deviation of the sampling distribution now, not the population, thank you, sir, shrinks. It's the same information, but we're pulling out samples of 9. Now, if you think about it, if I'm getting a sample of 9 and getting the average IQ of those 9, wouldn't we expect that to be right, that average to be in the middle someplace? That's why there's not as much spread. We're getting averages of groups of 9. If I randomly pick somebody in this room and just measured their height and did that over and over again, one at a time, those heights would be all over the place. But what if I got groups of 5 and got the average of those heights? Those averages wouldn't vary so much, right? Averages don't vary as much as individual things do. So that brings up something. We're talking about the population distribution. That's that drawing up there at the top. and we're talking about the sampling distribution. That's this one right here. We got two different distributions. Keep that in mind. So we got the underlying population, which looks like this. It's got its own average, its own standard deviation, its own shape. Well, this is a normal distribution, notice. And then we've got the sampling distribution. It's got its own average, its own standard deviation, its own shape. Here's where it gets confusing. You got to decide which one the problem's talking about. But I want you to know going in, some problems are talking about the population. I mean, sample size 1, right? I'm drawing one at a time. Some problems are talking about the sampling distribution. Here's a hint. If they're talking about just one person or one plant or one pen or one anything, they're talking about the population. If the sample size is 1, they're talking about the population. On the other hand, if the sample size is bigger than 1, then they're talking about the sampling distribution. That's your key right there. All right, and then we're reminded here, again, regardless of the size of the sample, the mean of the sampling distribution is the same as the population. And the standard deviation of the sampling distribution, that second distribution, is the standard deviation of the population divided by the square root of the sample size. Okay, it's right there in front of you. But the shape, that's a different thing. I'm going to show you something here in a minute. That population could be totally skewed. The shape could be skewed to the left or skewed to the right or just weird. But as the sample size goes up, the sampling distribution shape gets more normal. Don't confuse what I'm saying. Does it make the population more normal? No. The population is what it is. It could be totally skewed. But as the sample size goes up, now we're talking about the sampling distribution. As the sample size goes up, the sampling distribution gets more normal. That's good because then we can use z-scores and all sorts of stuff. And that second thing there is actually called the central limit theorem, which says we don't care what the population shape is. The sampling distribution shape of X bar, those averages, gets more and more normal as the sample size goes up. So we want a large enough sample size for our sampling distribution to be normal, so we can do z-scores in that table in the back and all that good stuff. That's called the central limit theorem. Caution. The central limit theorem does not have anything to do with the average or the standard deviation. All it's dealing with is the shape of the sampling distribution. This is why I wanted to print those things off for you. Not only to make the notes easier, but you've got something in front of you. This is a lot of stuff. All right, so the central limit theorem only has to do with the shape. Here's a for instance for you. Here's a distribution really skewed to the right. What's the sample size there? 1, because it's the population. If we sampled individuals from that population, we'd get a distribution that looks like that. There's the histogram for it. What happens when we raise the sample size from 1 to, what is it, 4? Look what's happening. Look at what is happening there. What did that histogram do? It's the same information, but now then, that second graph there, B, That's a sampling distribution. The one on the left is the graph of the population. The one on the right is the sampling distribution with a really small sample size. That sampling distribution is a whole lot closer to normal than the population was. Did we change the population? No, can't. It is what it is. All right, let's raise the sample size a little bit more. Look at that. Let's raise it a little more. Now, y'all, those last three drawings are of a sampling distribution, not the population. This is what the central limit theorem is talking about. As the sample size goes up, the sampling distribution shape gets more and more normal. How can that be? Okay, this is a deal that you can actually access. It's called StatCrunch, and it's really neat for doing experiments. So I'm just going to draw a population. Well, that population is kind of normal. So look at my sample size down there in that middle box on the right. It says sample size 1. So I'm going to draw a random, let's say these are heights or something. Well, the mean, look up here at the top, the mean of this distribution that I drew was 24.9855. I'm going to draw one. Okay, so what's going on here? That middle thing, there's my sample, and so far my sampling distribution down there looks just like what I drew. So let's do it again. Right? So those are two different samples. Look at the average of my samples down there. It's 12.1914. That's changing. Now, what if I did this over and over and over again? Let's do 5 of them. Each time it's one individual. What shape am I going to end up with if I did a bunch of these? Should be the shape of the population. Let's do 1,000 of them at once. Pretty normal looking. Let's do another 1,000. So as the number of samples goes up, we're up to what? 3,010 samples now. That's looking pretty normal. Well, you go, the population was normal to start with. So I can draw individuals and I'll end up with a pretty normal distribution because that's going to pretty well describe the population. Look at the mean of the population, 24.9855. Look at the mean of this green down here, 24.6. That's pretty close. Look at the standard deviation of the population, 10.1107. Look at it for my sampling down here, 10.0011. Getting pretty close. If we did this a few more times, this thing at the bottom is getting more and more and more looking like the population I drew. That's just taking one at a time. Let's reset. Let me draw another population here. This is far from normal. Would you agree? If I just take one at a time, what's my sampling result at the bottom going to look like? Should look like that thing. So let's do it one at a time just to start with. Can't really tell much from that. Let's kick it up to 1,000. 2,000. See, my sampling distribution when the size of the sample is 1 looks just like the population, doesn't it? If I kept doing that, it would look identical to the population. Let's reset. And I'm going to kick this up to just a sample size of 4. What's going to happen? the standard deviation is going to shrink. Let's do that 1,000 times. Y'all, I did not change the population. The thing in green down there is the sampling distribution of the averages. Let's do it again. Let's reset. Same population. If I did 5 at a time, okay? 5 at a time. Watch what happens. Let's just do it one time. So there's my 4 samples, and I get 1 average out of it. I got 4 little samples. That green thing at the bottom is the average of those 4 samples. If I do it again, I'll get another 4 samples. They're spread out. But the averages aren't. Do it again. 4 of them. They're spread out. But the averages aren't. So that's why when I repeat this, getting samples of 4 over and over and over again, look at my results. That's about as normal as you can get. So no matter what the shape of the population, once you start getting larger samples, the sampling distribution gets more normal. Okay, so let's do this. Let's raise the sample size. Let's reset with that weird population. Let's kick it up to 30. Let's just do one of those. Now there's 30 little samples in the middle, 1 average at the bottom. I'll do it again. 30 more samples. Let's kick it up to 1,000. Look at the standard deviation of, look at the top. The standard deviation of the population is 14.1768. What's the standard deviation at the bottom? Yeah, 2.6 something. What happened? That standard deviation came way in, grouped around the mean. Look how close the mean of the green distribution, the sampling distribution, is to the mean of the population. Pretty close. Okay, just want to show you that. That's in StatCrunch. Here's a handy dandy little flow chart for you. Section 8.1 is talking about averages, means. Section 8.2 is talking about proportions, like percentages. What percent of the people believe in the Easter Bunny, that kind of thing. Here's what you do. You first ask yourself, is that sample we're talking about, is it random? If the answer is no, then all this goes out the window. Are the samples independent? What does that mean? Is the sample size less than 5% or less of the population size? If you answer yes to both of those, you can continue. So I put the population information in green up there. It's got its own average, its own standard deviation, and the shape is whatever it is. But the sampling distribution, on the other hand, I'm saying the average here, and I should have put another little equal out here, that mu of x bar ought to be the same as, it might be written in on your copy, should be the same as the population average. And the standard deviation is the standard deviation of the population divided by the square root of n. The shape, we just saw this. If I'm drawing my samples from a normal population, my shape's normal. So if the underlying population is normal, I don't care what the sample size is, your sampling distribution will be normal. Well, what if you don't know about the population shape, or what if you know it's really badly skewed? Then as long as your sample size is at least 30, we're going to say, well, the sampling distribution is normal. So you got to ask yourself some questions here. Right, true or false? What do you think on the first one? Circle. Actually do 4, 5, and 6. Whether you think they're true or false, please. Do some interactive notes here. Okay, what do you think about 4? True. If we got a normal shaped population, our sampling distribution will be 2. What about 5? That's correct. And how about 6? That's the trickiest one. False. How big would the sample have to be? It'd have to be 4 times as big to cut the standard deviation in half. What does that mean? If my original samples were 10, n was 10, then to cut that standard deviation in half, I'd have to start taking sample sizes of 40 to cut it in half. All right, let's work some problems together here. We're looking for some of those magic words. Simple random sample. So one of those questions is this sample random? Yeah. It says of size 10. Well, if our population is at least, 200, then we're good with that 5% rule. So we're going to assume the population is at least that big. And so we can say, yeah, independent. Normally distributed. What's the shape of our sampling distribution going to be? Normal. The population, the sample size is 10. The population average is 30, and the population standard deviation is 8. Let's say, what's the sampling distribution? Well, we know the average is going to be the same as the population. We know the standard deviation is going to be the population standard deviation divided by the square root of 10. And the shape, normal. Okay, questions about that one? So we're looking for where's the center, what's the standard deviation, what's the shape. Look at number 8. Now we've got n equals 40. So let's look for some of those magic words. Simple random sample, that's what we're looking for. Size 40. So are we going to assume that the population is big enough that 40 is 5% of it or less? Yeah. Unless there's something in there to make us think otherwise. The population has an average of 50 and a standard deviation of 4. And then the question comes up, does the population need to be normally distributed for the sampling distribution to be normal? No, it doesn't. You're right. And it says, why? Good. Sample size is over 30, so the central limit theorem tells us that sampling distribution is going to be pretty normal. And then as for this sampling distribution, all right, I know the mean is going to be the same as the population. Look at the notation. This is mu of x bar. It's the average of the averages, if you will. The standard deviation is going to be 4 divided by the square root of 40. And the shape, normal. All right, let's look at gestation periods for humans. The average for the population is 266 days, and the standard deviation is 16 days. That's for the population. Part A says, what's the probability a randomly selected pregnancy lasts less than 260? All right, I'm seeing randomly selected, so that's good. I'm pulling one pregnant woman out of the population. I think that's less than 5%. Of course, we're just talking about the population here, aren't we? So what am I going to do? I'm going to do a z-score. Put 260 minus 266 divided by the standard deviation, and I'm getting a z-score of negative 0.38. And I went ahead and looked this up in the formula pages. So the probability that that one person that I drew out carries that child less than 260 days is about 0.3520. I got that from the table. What's that telling us? That in this population, about 35% of women carry the baby 260 days or less. Okay, we're going to change that up now. We're going to get a random sample of 20 pregnant women. And we're going to get the average time that they carry the kids. Now then, that average is going to be squished down, right? Because we got 20 of them. Describe the sampling distribution. Well, I know the average is going to be the same as the population. I know the standard deviation is going to be 16 divided by the square root of 20. What's the shape going to be? That sample size is not at least 30. Got to read the question. What's the first sentence in there? The length of human pregnancies is approximately normal. So the underlying population is normal. So that means this is going to be normal too. If you're drawing from a normal population, the sampling distribution is normal. And then it's saying, well, what's the probability those 20 pregnancies, the average of those 20 pregnancies is less than 260? Think it's going to be higher or lower than 35%? So I get a z-score. Notice it starts off just the same, but look at the denominator here. It's the standard deviation of the sampling distribution. Part A in this question was talking about the population. Part C is talking about the sampling distribution. All right, I worked that out, and I'm getting this. Now look at the z-score. Negative 1.68. That changed drastically from the negative 0.38 up there at the top. So I look it up in the table, and I'm getting the probability that this average of less than 260 would happen less than 5% of the time. If I'm getting samples of size 20, an average of those would average out to be less than 260 days, only less than 5% of the time. Why? Because the standard deviation is pulling in. Let's look at another one. Okay, give you a second to read this. So they're saying it's a 10-minute oil change place, but the average is really 11.4 minutes. And they're telling us some other information. The population is skewed to the right. the average is 11.4, and the standard deviation is 3.2. It says if we want to get a sampling distribution that's normal, how big would our sample have to be? At least 30. Remember, if the sample size is 30, then we can assume that the sampling distribution is normal. Part B, which distribution is that talking about? The population or a sampling distribution of averages? You have to decide. A random sample of 40, oh, okay, that's more than one, so now I'm talking about a sampling distribution there. So the first thing I do is sketch a little picture. They're wanting the probability that the average time of those 40 oil changes is less than 10 minutes. So I'm going to shade in the part that I want here. Please make a drawing. It'll help you because this is really easy to mess up. Okay, so I've got my sketch. I get a z-score. But notice the denominator is the population standard deviation divided by the square root of the sample size. Okay, I do the computations. I'm getting this. Now look at the z-score. Negative 2.77. Is this going to happen very often? No. No, it's way out there. It's almost 3 standard deviations to the left of the mean. So the probability of the average being less than 10 is less than 3 out of 1,000. So they're claiming this is a 10-minute oil change, but the probability of that sample of 40 averaging 10 minutes or less is 3 out of 1,000. Not very likely. And so start getting in your head, how likely are these things to happen? Because that's going to help us with the stuff we're going to talk about after spring break. Okay, so now then, same facility. The manager says, I'm going to give you all a $50 bonus if you reach a certain goal. And so on a typical Saturday, they're going to do 40 oil changes. We're going to treat that as an SRS, so there's something to look at. I don't know here. The question's saying, what average oil change time would there be a 10% chance of being at or below? I don't know that value. I'm going to be looking for it. And that's what the manager says we're going to have to meet to get our $50 bonus. So I know I want this area right here. So the area I'm looking for is 10%. I got to translate that to a z-score. So I go to the table, I look it up, and it turns out that's a z-score of this, negative 1.28. If I were you, I would take the time to do that later on, make sure my numbers are right. Okay, so now I'm going to use that z-score, and I'm going to say negative 1.28. Look what I'm doing. I've got 4 variables there, and I know 3 of them. I can solve for the 4th. Notice I'm saying X bar because it's an average that we're looking for here. So I start working it out. I multiply both sides by 3.2 divided by the square root of 40. I'm getting this. Then I add 11.4 to both sides. I'm getting this. What's that mean? No pun intended. It means that to get our bonus, we've got to average basically 10 minutes and 45 seconds for all 40 of those things. Some of them could be a little over, some of them could be a little under, but we're going to have to average 10 minutes and 45 seconds to get our bonus. You think that's going to happen? No. Not when we just saw that 10 minutes or less is less than 3 out of 1,000. Thank you, manager, for nothing. So we're going to be working our tails off. We're not going to make it. Sounds like coaches I used to have. All right, let's look at another one. It needs 2 minutes to look at this one. Okay. Approximately normal, these reading speeds, and both of these are random samples. A, what are we talking about there? The population or a sampling distribution? A, randomly selected student. What's the sample size? 1. So we're talking about the population. Okay, so what do? Here's my drawing. And we'll read more than 95, so I color in that right there. Please take the time to do that. Because what does that tell me? That tells me I've got to subtract what I find in the table. I've got to subtract that from 1. All right, so I'll start getting my z-scores. Notice I'm just using the population standard deviation there of 10 because we're talking about the population. I look that up in the table, and I'm getting this. So if we pulled a random kid out, the probability that that one kid can read more than 95 words per minute is about 31% of the time. Hang with me for just the end of this one. Make sense? We're talking about the population. What is C talking about? I skipped some. A random sample of 24 second graders. Now what are we talking about? Sampling distribution. You're right. So this starts off the same. My drawing would be the same, except now look at the new standard deviation. It's the population standard deviation divided by the square root of the sample size. I know that's going to make a difference. Whoa. Slightly. Look at the z-score. Is this going to happen very often? So the probability that this average of 24, remember I've got to subtract what I get from the table from 1. So if I just start pulling groups of 24 out of the population and averaging their reading scores, their reading times, I would get a group of 24 that averaged more than 95 words per minute 7 times out of 1,000. All right, thank y'all.